This is lecture video 33. In this lecture, we study the definite integral of a function over a closed interval AB, the properties of the definite integral, and its geometric interpretation. Okay, let's look into this notation in more details. This sign is the integral sign, and a and b are the lower and upper bounds of this integration. Our function is here inside the integration sign, and the integration sign will always be considered together with this dx notation. Okay, and altogether, this notation is called the definite integral of a function over a closed interval AB. And the result of the definite integral is always a number. Okay, so you will find a number. On the other hand, there is also this notation, which we will see soon in the upcoming chapters. Without the upper lower boundaries, this is called indefinite integral. And the result of it is, in fact, not a number, but a function. Okay? Here you will find a number, but here you find a function depending on x. So this one is called as the definite integral, which is the topic of this lecture video. Okay, after looking into the notation with more details, now we can try to understand the properties of it. But before that, let me also put some remark here about the geometric interpretation. If your function is here, f of x, is a non-negative function like this definite integral, as we covered in the previous section, has a geometric interpretation. The definite integral of this function, f of x over the closed interval AB, corresponds to the area under the curve. Okay, if this area is 8, the result of this definite integral will be the number a. Okay, let's move on. Here we see a very useful theorem about the integrable functions. It says if a function is continuous over an interval, or if has at most finitely many jump discontinuities. What does this mean, jump discontinuity? So, for example, this is a jump discontinuity of a function, right? And if your function is continuous, or it may have finitely many jump discontinuities like this, for example, at the point here and here, this function has a jump discontinuity, but you still can compute the integral of it from 0 to 5, let's say, over this closed interval. This function, even if it is not continuous, even if it has jump discontinuities like this, it is still integrable, okay? It is still possible to compute the definite integral of this function. This is what this theorem tells us exists. And if this integral exists, then you call your function as the integrable function. Okay, then what we have, this table shows you the properties of the definite integral. Let us go over it. Let me go over it one by one and try to understand them. Here, in the property 1, what does it say? If you have this definite integral from a to b, and if you reverse or if you switch the upper lower boundaries like this, you switch the places of them, then you look at the definite integral from b to a, and you have to put this minus sign in front, okay? If you switch the boundaries, let's say you have a definite integral of your function like that. And if you want to exchange the places of the upper lower boundaries, you need to put this extra minus sign in front. This is the first property of the definite integral. Okay, what is the second property? It is saying that if you compute the definite integral of your function from 3 to 3, from same point to the same point, from one point to the same point, then you will obtain nothing. The result will be just 0, okay? And third property, saying that if you have constants in front of your functions inside the integration sign, then this constant, as long as it is a constant with respect to x, you can take it out like this, k times the definite integral of your function again. Okay, so this is a very natural thing to do. If k does not depend on x, you can just take it out. What is the fourth property? Okay, fourth property says that integral notation respects addition and subtraction. Okay, you can just distribute integral over sums and subtractions. Okay, and maybe I can put a particular example on that here, like consider this definite integral, please. You see, this is a sum of two functions. Then you can rewrite it as the integral of the first function plus the integral of the second component of this overall sum, which means you can distribute the integral sign over the sums and also over the differences like this. Okay, let's move on to the fifth property. What is it? Yes, this is also another important property, that integration sign is additive. So here we go. Let's write a particular example of that. If you integrate from 1 to 2 f of x dx, and then you continue from where we left, like from 2 to 5, f of x dx, then it is possible to write this integral in just one integral sign from 1 to 5, okay? And you can understand that by using the geometric interpretation of the integral. So what we are doing is, let's say f of x is a non-negative function. So first, we are taking the integral of it from 1 to 2, right? So we computed this area. Let's call it as A1. And then what we do, we compute another integral from 2 to 5. Let's name that area as A2. Okay, this is A1, the area under the curve. You remember the definite integral gives us the area under the curve, and this part is the area A2. So if you integrate from 1 to 5, of course, you will get the same integral because it is the area under the curve from 1 to 5, which are the sums of those areas, right? So geometrically, it can be seen easily like this. What is the sixth property? So this time, we assume that f has a maximum value and minimum value over an interval. Then the result of this definite integral is between this lower bound and upper bound, where you multiply the length of the interval on the left side by the minimum value. This is the length. This is the length, and on the right, for the upper bound, you multiply it with the maximum value of f. Again, by using geometric arguments, we can understand this property. So let's say you have such a function. Okay, and let's consider this function over the interval AB, like that. And here, as you can see, this is the highest value of your function, which is the maximum value of f, described in the statement. So this is maximum value of f, right? And this is, let's call it as the big letter f, okay? M is in fact the maximum value of f. And here, right at this point, this is the absolute minimum value of your function. Let's denote it by the small letter f, absolute minimum of f. Now, we want to consider this definite integral and try to construct an upper and lower bound of it, depending on small letter m, big letter m. First of all, if, okay, let's consider the area of this big rectangle. It is what? It is b minus a times the big letter m, right? And now let's consider the area of this smaller rectangle, which is again, okay, b minus a Okay, sorry. Let's put it like b minus a. This green rectangle has this area times m. And the blue rectangle overall, the big one, is in fact b minus a times the big letter m. And as you can see, the area under our curve is between the area of this bigger rectangle and the area of this smaller rectangle. That's why we can safely put this upper lower bounds. And this is the area under the curve. That's why the definite integral is always between these two numbers, where m is the minimum value, absolute minimum value, and this is the absolute maximum value of your function f. Okay, area of the green rectangle. And this is the area of the bigger blue rectangle. Okay, this is a property 6. And finally 7, it says what? It says if you have such an ordering between your functions, okay, then the definite integrals will have the same order. Okay, let's go over it. Again, let's assume that your functions are non-negative. And let's say f has this graph where g has this graph. And if you integrate them over this closed interval AB, what happens? The definite integrals. Okay, so like this, we are concentrating over the closed interval AB. So this is this area under your curve f of x, and this, okay, a to b f of x is the area under the blue curve, and a to b g of x is the area under the black curve. That's why, as you can see, since the f of x curve is bigger than the g of x curve, the definite integral of it will also be bigger than the definite integral of the g of x. So the conclusion is, if you have such an ordering between your functions, this happens. And if the function is always positive, where you take now g of x as 0, what will happen? Its integral will always be non-negative, because there will always be an area under your curve. Okay, this is the summary of the last property. Now we can start solving some particular examples. Look at this example. The integral of f of x from 1 to 2, definite integral, is given as 5. Then what is this? This is nothing but writing the same definite integral in the notation of u. No difference, okay? Instead of your independent variable x, you can use other variables like u, t. It doesn't matter. So this is still 5. Or you can even write it in terms of other variables with t, still 5. It is just change of notation. And what is this then? Again, 5. So use the properties. This square root 3 is a constant with respect to z. So you can take it out. It is square root 3, 1 to 2 fz dz. So another change of notation. So square root 3 times 5. And here, this minus is kind of a constant. You can take it out, right? It is minus 1 to 3 f of x dx, so minus 5, obviously, because this part is given as 5. So let's move on. It says, use maximum minimum inequality to find an upper lower bound of this definite integral. So we want to use the property given here in the 6th item. So a definite integral is between these two values, where this is the bigger rectangle and this is the smaller green rectangle. We want to apply that property for this function. That's why we need to compute the absolute max and absolute minimum of this function over the given interval 0, 1. So 1 plus x squared. How do you find absolute max? Means you first find critical points of it, right? Which is minus 2x. This is the first derivative of your function. And first derivative is 0 when x equals 0. First, is there any point where first derivative is undefined? No, there is no such point. No point coming from here. Now you create your list of points where this is coming from the critical points. By the way, the interval is 0, 1 interval, so you should take this endpoint too and look at the images of your function on those endpoints. So f0, insert 0 here, 1. F of 1 is 1 over 2. Insert just 1 here, 1 over 2. So you see this is the absolute maximum value as the biggest value of your function. So absolute maximum value, we will take the big letter M in that statement as 1. And this is the absolute minimum value of f. Let's name it as small letter f. Now use the property. The definite integral of this function should be between length of the interval b minus a, 1 minus 0, 1 minus 0, times small letter m, big letter m, right? Where we computed this as 1 over 2. Sorry, this should be 1 over 2, right? And this as 1. That's why we obtain these upper-lower bounds for our function. So the definite integral is, in fact, don't forget to put the x every time, okay? So it is between 1 and 1/2 by using the sixth property given above. Okay, so now I guess we can move on. Area under the graph of a non-negative function, we use this idea several times. This definition tells us that if you have a non-negative function, okay, not being non-negative is important here, over a closed interval, if you take the definite integral of this non-negative function, dx, then you will find a number for sure, and that number has a geometric interpretation, which is the area under the curve. Under the curve, y equals f of x over the interval ab, so it will be exactly the area much. Okay, and finally, if you have an integrable function, you can define the average value of it like that. And this this equality is something that we have covered before. So average value of f is, in fact, you see, this is the area under the curve. Okay, you can rewrite it as area under the curve divided by the length of the curve, okay? Length of the interval. Now, as we defined area under the curve with the definite integral, the average value of function can be rewritten like this with the definite integral notation. And let's handle this final example, which is about the average value of function. Our function is this one, and we want to compute the average value of it over this closed interval, okay? So average value of f over the given closed interval is what? The definite integral over that closed interval of the given function divided by the length of the interval, which is 3 minus 0. Okay, let's now concentrate on this definite integral. Let's compute this definite integral. Okay, let's concentrate on it. 0 to 3 minus f of, okay, let's write f of x dx first. F of x dx is from 0 to 3 minus x squared over 2 dx. And now for the first time, I will introduce the idea of how to compute definite integrals by using antiderivatives, okay? Definite integral is in fact nothing but the same as the antiderivative that we covered before at the end of the previous section. So the result of this definite integral is the antiderivative of this function. Okay, you need to tell me a function now whose derivative is this thing. Remember? So you are taking antiderivative now. So such functions are called antiderivatives, and computing definite integral is the same as computing antiderivative. So now we need to consider a function, big letter f, whose derivative is f. So, and in fact, we know how to take the antiderivatives like this. And before writing the result, maybe we can rewrite this integral by using the properties. -1/2 is just a constant there, right? That's why you can take it out like this. And after taking this -1/2 constant out, it will be much more easier to find the antiderivative of x squared. Okay, tell me a function whose derivative is x squared. Of course, you add 1 to the power, divide by the same power. So this was the rule for taking antiderivative of the power functions. And then, since this is a definite integral, you have to put these boundaries like here and here to find the result as a number. This notation means what? This notation means that you first insert 3 for x. Okay, you first insert 3 for x, then insert 0 for x to the result, and you take the difference. Okay, this notation means applying like that. So the result is, and by the way, there was this one -1/2 in front, so that the result is -27/6. So, and then the average value is the result of this definite integral -27/6/3. Okay, so the result is like that, where we computed here. Okay, I stop here. Thank you for your attention.